previous class I was teaching you about bipolar junction transistor. Transistor, it is known as bipolar because it contains types of carriers that are electrons and holes. Okay, that is why a transistor it is known as bipolar junction transistor. Okay, and it is a 3-terminal device. Okay, so there are 3 types of configuration. First one is common base configuration, second one is common emitter configuration, and the third one is common collector configuration. So we can connect the transistor in either common base configuration or common emitter configuration or common collector configuration. Okay. So this is the circuit diagram for common base configuration. So in common base configuration, this is say emitter, this is base, and this is collector terminal. These are the 3 terminals: emitter, base, and collector. Okay. So a BJT is a 3-terminal device. Okay. And in common base configuration, the base terminal is common to both input as well as output. Okay. That is why it is known as common base configuration. And this is PNP transistor. Okay, so it is in common base configuration. Okay, so this is the circuit diagram. This is PNP, this is P and P, and this is emitter, base, and collector. This is emitter, this is base, and this is collector. Okay. Now, the direction of collector current it will be like this, and the direction of base current, it will be like this. This is IB, and this is the direction of collector current. Okay, and it is biased by using external voltage VEE and VCC. RC is the load resistor. Okay. Then this is NPN transistor. Again, this is emitter, base, and collector, and it is connected like this. This is N, P, and this is N. This is emitter terminal, this is base terminal, and this is collector terminal. Okay. Now the direction of current flow. This is IE. Okay. The direction of IB it is like this. Okay, and the direction of IC it is like this. So here IC it is in this way, IB it is like this, and similarly IE it is like this. Okay. So PNP transistor and NPN transistor both are in common base configuration. Okay. So in common base configuration transistor, we will have to study about the input characteristic curve and output characteristic curve. Okay. And these are biased by these voltages VEE and VCC. Okay. So first of all, we have to study about the input characteristic curve. Okay. So this is the input characteristic curve. Input characteristic curve, you can see here, input current is IE. This is input current, and VEB. VEB it is E and B. So voltage across these 2 terminals it is VEB. So it is the graph. It is the graph between input current versus input voltage for different values of VCB, means for different values of this output voltages. This is VCB. Okay. So how we can get the input characteristic curve? This figure is say figure 1. This is input characteristic curve. Okay, and this figure 2, this is output characteristic curve. Okay, so output characteristic curve, it is the graph between output current. Output current here it is IC. In case of common base configuration, the output current is IC versus VCB, means the output voltage for different values of input current. So input current it is IE. So we can define the input characteristic curve it is the graph between input current versus input voltage for different values of output voltages. So here output voltage for different values of VCB. We can write for different values of VCB. Okay. So there are two types of characteristic curve. First one is input characteristic curve and the second one is output characteristic curve. Input characteristic curve, it is the graph between input current versus VEB for different values of VCB. Okay, and output characteristic curve, it is the graph between output current, that is IC, versus VCB for different values of IE, for different values of the input current. Okay, so from the input characteristic curve we can determine the input resistance. From input characteristic curve we can determine the resistance. So Ri, that is input resistance, it is equal to del VEB divided by del IE for constant value of VCB. Okay. So in this way, from the input characteristic curve we can determine the input resistance of the device. It is equal to del VEB, this VEB divided by del IE for constant value of VCB. Okay. So from this figure we can see that for a small change in VEB, a large amount of IE is found. Okay. So you can see in the figure, see, for a small change in VEB we can get a large change in IE. So Ri is very small. It is very small because for a very small change in VEB we are getting a large change in IE. So that is why the Ri, it is very small and it is in the range of few ohms. Okay. Then we will study about the output resistance. How we can determine the output resistance of the device from output characteristic curve. Output characteristic curve. From output characteristic curve, how we can express the our output, that is output resistance. So it is equal to del VCB divided by del IC for constant value of IE. Okay, it is del VCB divided by del IC for constant value of IE. And here in this figure we are seeing that this is almost horizontal, this graph. Okay, so this graph, this is saturation region, this is active region, and this is cutoff region. So cutoff region, it will start from IC is equal to 0. Okay, so there are three regions. In cutoff region, both the junctions, that is emitter base and collector base, both are reverse bias. In saturation, both the junctions are in forward bias. In active region, this emitter base, it is forward bias, and collector base, it is reverse bias. So in active region of operation, one is forward bias and the other one, that is emitter base, it is forward bias, and collector base, it is reverse bias. Okay, so for amplification purpose, the transistor is generally operated in the active region. Okay, now we can get output resistance from the output characteristic curve by using this formula. So it is del VCB by del IC for constant value of IE. Okay, now from this equation, it is evident that you can see for a large change in VCB, IC is almost constant. So del IC, it is very small. For a large change in VCB. You can see, if in this figure, for a large change in VCB, IC is almost constant. That is why our output, it is very high. So we can see that from the output characteristic curve, we can determine the value of output resistance. It is equal to del VCB divided by del IC for constant value of IE. Okay, so it is very high. Because why it is very high? Because for increase in VCB, change in IC is very minimum, because it is almost horizontal. Okay, so change in IC, it is very minimum with the change in VCB. So it is very high, and it is in the range of several kilo ohms. Okay, about the collector current. Expression for collector current in common base configuration. Okay, as we know that IE, it is equal to IB plus IC. As we know that IC, it is equal to IB plus IC. Okay, the current amplification factor, it is equal to IC divided by IE. It is equal to the current amplification factor. So normally in case of common base configuration, alpha, it varies from 0.9 to 0.99. Okay, and its value is always less than unity. Now we can write IC it is equal to alpha times IE, alpha times IE plus ICBO. We have seen in output characteristic curve, if IE it is equal to 0, if IE is equal to 0, then what will happen? If IE is equal to 0, then IC it is equal to ICBO. So what is ICBO? ICBO it is reverse leakage current between collector and base when emitter is open. It is the reverse leakage current between collector and base when emitter terminal is open. Okay, so we can draw a figure like this. Suppose this is base terminal, this is collector terminal, and this is emitter terminal. Suppose this is open. If it is open, then in that case IE it is equal to 0. Okay, then it is ICBO. So ICBO is the reverse leakage current between collector and base when the emitter terminal is open. So if emitter terminal is open, then in that case IE it is equal to 0. So if IE is equal to 0, then IC it is equal to ICBO. So this is the reverse leakage current in case of common base configuration. So in case of common base configuration, write IC it is equal to alpha IE plus ICBO. Okay, and we know that IE it is equal to IB plus IC. So we can write this equation. Suppose this is equation A, so we can write it is equal to alpha into IB plus IC plus ICBO. Okay, now it is equal to alpha IB plus alpha IC plus ICBO. Okay, now we can write IC into 1 minus alpha, it is equal to alpha IB plus ICBO. Okay, from this we can get IC it is equal to alpha divided by 1 minus alpha IB plus ICBO divided by 1 minus alpha. So in common base configuration, this is the expression for collector current in case of common base configuration. Okay, so from this expression we can determine the value of IC. Here alpha is the amplification factor in case of common base configuration, and ICBO, it is the reverse leakage current between collector and base when emitter terminal is open. So if emitter terminal is open, then emitter current it is also equal to 0. Then in that case it is very less. Okay. So this is the expression of collector current in common base configuration. Okay. Now we will study about common emitter configuration. So in case of common emitter configuration, emitter terminal, this is the emitter terminal. Emitter terminal is common to both input side as well as to the output side. That is why it is common emitter configuration. Okay. So in common emitter configuration, suppose this is N, P and N. Okay. This is emitter, this is base and this is collector terminal. Okay. And this is forward bias and this is reverse bias. In normal case, this terminal, that is base and emitter, this is forward bias and this is reverse bias. Okay. So here it is, we can see that this is P is connected to positive and N is connected to negative terminal. That is why it is forward biased, and this junction it is reverse bias. Okay. N is connected to positive terminal. Okay. So this is reverse bias. Okay. This is for the transistor used here, it is NPN transistor. This is for NPN common emitter configuration, and this is PNP common emitter configuration. Okay. Now you can see this arrow. What is the use of this arrow? The use of this arrow is that it gives the direction of IE. Suppose this transistor, this is NPN transistor, this is emitter, this terminal is base and this terminal is collector terminal. This is NPN transistor. So what does this arrow signify? This signifies the direction of emitter current or conventional current. Okay. So this is for NPN. For PNP, the arrow will look like this. Okay. So the direction of IE, it will be like this. IE for PNP. Okay. Now again we can see here, in case of NPN common emitter configuration, this is forward bias and this collector and emitter junctions are reverse bias. Okay. For this case also, this is for PNP, this is forward bias and this is reverse bias. And this is the input signal that we want to amplify. So the output voltage, we can get it across RC. The amplified voltage we will be getting across RC. Similarly, this V out we will be getting across RC. Okay. So again, in common emitter configuration, we have to study about the input characteristic curve and output characteristic curve. We have to study about input characteristic curve okay. So and output characteristic curve. Output characteristic curve. Okay. So input characteristic curve, it is the, you can see here, input characteristic curve, it is the graph between input current versus input voltage for different values of VCE. For different values of VCE, it is IB versus VBE for different values of VCE. Similarly, output characteristic curve, it is the graph between IC versus VCE for different values of IB, for different values of input current. So here IB is input current and IC is output current. Okay. Again, in this figure we are seeing three regions of operation. First one is saturation region, this is active region, and this is cutoff region. Amplification of signal can be achieved in active region of operation only. Okay. So from the input characteristic curve we can determine the input resistance Ri. It is equal to del VBE divided by del IB for constant value of VCE, when VCE is equal to constant. Okay. Now we can see Ri, the expression for Ri, it is equal to del VBE divided by del IB for constant value of VCE. So as compared to common base configuration, here input resistance Ri is high as compared to common base configuration. Why it is high? Because see, IB it is in the range of microampere. Okay, so change in IB will be very less with change in VBE. So here it is less, here it is more, so it will be definitely higher quantity. Okay, so as compared to common base configuration, Ri of common emitter configuration it is high. Okay, then we will study about output characteristic. From the output characteristic curve, how we can determine output resistance. Output resistance, it can be determined from output characteristic curve. Okay, so our output it is equal to del VCE divided by del IC for constant value of IB, when IB is equal to constant. So here we can see from this output characteristic curve we can determine the output resistance. Okay, so in the output characteristic curve we are seeing that this slope is higher as compared to common base configuration. In common base configuration the output was horizontal, but here we are seeing that here it is having some slope. Because of this it has lesser output resistance as compared to common base transistor. Okay, because in case of common base configuration curve was like purely horizontal, but here we are seeing that it is having some slope. That is why it has lesser output resistance as compared to common base configuration. Okay. Then we will study about beta. What is beta? So beta is current amplification factor factor in common emitter configuration. How we can define beta? Beta, it is equal to the output current. So in case of common emitter configuration, output current is IC to input current. Input current is IB. Okay, so it is equal to output current divided by input current. Okay, so this is beta DC. Similarly, if we want to determine beta AC for AC signal, so it will be del IC for del IB, okay, for constant value of VCE, it will be constant. So again, for in case of common base configuration, alpha for DC, it is equal to output current. Output current, it is IC, input current is IE. Okay, again alpha AC, it is equal to del IC by del IE for constant value of VCB when it is equal to constant. Okay, alpha DC, alpha AC, beta DC and beta AC. Okay, then we will see about the relation between alpha and beta. Okay, now as we know that beta, how we can define beta? Beta is equal to del IC divided by, how this is beta, it is in case of common emitter configuration. This is the current amplification factor in case of common emitter configuration. So it is del IC divided by del IB. Similarly, alpha, it is equal to del IC divided by del IE. As we know that IE, it is equal to IB plus IC. We can write. Then we can also write del IE, it is equal to del IB plus del IC. Okay. Now from this equation we can write del IB, it is equal to del IE minus del IC. Okay, this is say equation A. Now 1 by delta IB, it is equal to 1 divided by del IE minus del IC. Suppose this is equation B. Okay, now equation B, it is if we are multiplying delta IC. Okay, so it will be del IC here. Again, here we have to multiply with del IC. Okay, so it will be del IC by del IB. It is what? It is equal to beta. Beta is equal to del IC divided by, again we can divide with del IC and again del IC. So it will be 1 divided by del IE by del IC. It is equal to 1 divided by alpha minus 1. Okay. So from this beta, it is equal to 1 divided by 1 minus alpha, it is equal to alpha. From this expression we are getting beta, it is equal to alpha divided by 1 minus alpha. So this is the relationship between current amplification factor in case of common emitter configuration and in case of common base configuration. Okay, as we know that the value of alpha, it lies between 0.9 to 0.99. Okay, so from this expression we can see beta is equal to alpha divided by 1 minus alpha. So beta is very high and its range is from 20 to 500. Normal range 20 to 500. Okay, and see alpha, it is generally less than 1. So beta, it is its value, it is very high as compared to alpha. So current amplification factor in case of common emitter configuration, it is very high because beta is high. Okay, we can express the collector current. In common emitter configuration. Okay, IE, it is equal to IB plus IC. We all know IE, it is equal to IB plus IC. Okay, IC, it is equal to alpha IE plus ICBO. Okay, and it is equal to alpha. What is this IE? IE is here. IE, it is equal to IB plus IC. IB plus IC plus ICBO. This expression we have seen in common base configuration. Okay, but we have to find the expression for collector current in common emitter configuration. Okay, so it is equal to alpha IB plus alpha IC plus ICBO. It is equal to IC. Okay, so IC 1 minus alpha is equal to alpha IB plus ICBO. Okay, so from this we can write IC, it is equal to alpha divided by 1 minus alpha into IB plus ICBO divided by 1 minus alpha. Then from this we can write IC, it is equal to beta times IB plus ICBO divided by 1 minus alpha. Okay, if IB, we can see if IB it is equal to 0, then what will happen? Then IC, it is equal to ICBO divided by 1 minus alpha. It is reverse leakage current between collector and emitter when base is open. Okay, so this ICO, it is equal to ICEO. Okay, so how we can write? It is equal to beta IB plus ICEO, where ICEO, it is equal to ICBO divided by 1 minus alpha. Okay, ICBO is the reverse leakage current between collector and base when emitter terminal is open. It is the reverse leakage current between collector and emitter when base is open. And this ICEO is very much larger than ICBO, because here in the denominator it is 1 minus alpha. So this quantity it will be in fraction, so it will be very much high as compared to ICBO. Okay, so we can see how to calculate ICEO. Suppose this is an PN transistor in common emitter. This is collector terminal and this is emitter terminal, and the base is open. So if base is open, this is base terminal, this is collector terminal C, and this is emitter terminal. So if base terminal is open, what does this mean? Then IB is equal to 0. So if IB is equal to 0, whatever be the value of IC, it is equal to ICEO. Okay, it is ICEO. So ICEO is the reverse leakage current between collector terminal and emitter terminal when base is open, when base terminal is open. So if base terminal is open, then in that case IB is equal to 0. So in this way we can determine or we can measure the value of ICEO, and it is very high as compared to ICBO.